Open Google Maps. Find any major airport. Zoom in. Look at the runways. Now look again. One runway points northeast to southwest. Another points directly north to south. A third cuts across both of them at a completely different angle. From above, it looks like someone dropped the design and reassembled it without instructions. No obvious logic, no obvious symmetry, no obvious reason why three strips of concrete couldn't at least agree on a direction, and yet every single one of those angles was chosen precisely, calculated, approved, built to face exactly where it faces, for a reason that has nothing to do with the shape of the land and everything to do with something invisible: the wind. Here is what almost nobody considers when they look at an airport from above. An aircraft cannot land in any direction it wants. It needs to land into the wind, not with the wind behind it, into it. And that single requirement, land into the wind, dictates the entire geometry of every airport ever built. To understand why, you need to understand what a tailwind does to a landing aircraft. At touchdown, an aircraft is moving at approximately 240 to 280 kilometers per hour relative to the air around it. That is airspeed. Speed relative to the atmosphere. But what matters on the runway is ground speed. Speed relative to the concrete beneath the wheels. Headwind subtracts from ground speed, tailwind adds to it. A 30 km per hour headwind means the aircraft touches down 30 km per hour slower relative to the runway. Shorter stopping distance. More margin. A 30 km per hour tailwind means the aircraft touches down 30 km per hour faster relative to the runway. Stopping distance increases dramatically. Margin disappears. Most commercial aircraft have a maximum allowable tailwind component for landing of 10 to 15 knots, approximately 18 to 28 kilometers per hour. Beyond that limit, the aircraft cannot legally land on that runway in that wind condition. So when the wind shifts, when the prevailing direction changes, the airport needs a runway that points into the new wind. This is why airports have multiple runways pointing in different directions. Not poor planning. Wind coverage. Now let's look at how that coverage is calculated before a single meter of concrete is ever poured. Airport planners begin with a windrose. A windrose is a circular diagram that shows the frequency and strength of winds from every compass direction at a specific location, compiled from years, sometimes decades, of meteorological data. The goal is to select runway orientations that provide usable wind conditions for the maximum possible percentage of annual operating time. The international standard, defined by ICAO, requires that the runway system provide coverage, meaning wind conditions within the allowable crosswind and tailwind limits, for at least 95% of the time. That 5% of unacceptable conditions is the design allowance for weather so severe that operations would be restricted regardless. At many locations, a single runway oriented into the dominant wind direction achieves 80 to 90% coverage on its own, but 80 to 90% is not 95%. The gap, the remaining 10 to 20% of time when the wind comes from a direction that makes the primary runway unusable, requires a second runway, oriented differently, covering the wind directions the primary runway cannot serve. At airports with highly variable wind patterns, coastal locations, mountain valleys, continental interiors where seasonal pressure systems rotate the dominant wind direction, a second runway, oriented roughly perpendicular to the first, provides the most efficient additional coverage. This is the crosswind runway. It does not need to be as long as the primary runway. It does not need to handle the heaviest aircraft. Its sole purpose is to provide a legal, safe landing direction during the percentage of time when the primary runway is wind limited. Chicago O'Hare International Airport is the most cited example of this logic taken to its extreme. O'Hare sits in the flat interior of North America, exposed to wind patterns that rotate significantly with passing weather systems. The airport has runways pointing in two primary directions, roughly east-west and northwest-southeast, with multiple parallel strips in each direction for capacity. From the air, it looks chaotic. On the ground, it is a precisely tuned wind coverage system that keeps the airport operational through the full range of Midwest weather patterns. But wind is not the only variable. Runway direction is also constrained by obstacles. Hills, buildings, communication towers, restricted airspace. All of these define the approach and departure corridors available to each runway. A runway cannot be oriented toward a hillside, even if the wind data says it should. A departure path cannot overfly a restricted military zone, even if the geometry is otherwise perfect. The final runway layout is always a compromise, the best achievable wind coverage within the constraints imposed by terrain, airspace structure, and the surrounding built environment. Now, let's look at the numbers painted on every runway and what they actually mean. Every runway has a 2-digit number at each end. Those numbers are the magnetic heading of the runway divided by 10, rounded to the nearest whole number. Runway 27 points approximately 270 degrees, due west on a magnetic compass. Its opposite end is runway 09, pointing approximately 90 degrees due east. Runway 36 points due north, 360 degrees. Runway 18 points due south, 180 degrees. When a runway is labeled 1432, it means one end faces approximately 140 degrees southeast and the other faces approximately 320 degrees northwest. These numbers are not fixed permanently. The Earth's magnetic field drifts slowly over time, a process called magnetic declination change. As the magnetic North Pole migrates, the magnetic heading of a fixed physical runway changes. When that drift accumulates enough to shift the rounded heading number by 1 unit, 10 degrees, the runway is officially renumbered. Airports periodically close briefly to repaint runway numbers as the magnetic field shifts. Los Angeles International Airport renamed its runways in 2009 due to accumulated magnetic declination change. London Heathrow renamed its runways in 2022 for the same reason. The concrete did not move. The planet's magnetic field did. Now, consider what this system means for daily operations. Air traffic controllers assign runways based on current wind conditions. At an airport with parallel runways in two directions, the active configuration changes throughout the day as wind patterns shift. Morning may favor the east-west runways. Afternoon sea breeze may shift operations to the north-south configuration. An approaching weather system may force a complete reconfiguration midday. Every aircraft in sequence rerouted, every approach procedure changed, every departure path adjusted. This reconfiguration is not exceptional. At weather-affected airports, it happens multiple times per week. The infrastructure exists to make it possible. The runways point in different directions so that when the wind changes, the airport does not close. It simply changes direction. The geometry that looks random from satellite view is the physical answer to a meteorological question. How do we keep this airport open regardless of which way the wind is blowing today? The answer is concrete, pointing in every direction the wind requires, calculated to the degree, built to last decades, renamed when the planet itself drifts. Every confusing angle on that airport map is a wind direction that someone measured. a coverage gap that someone calculated, and a runway that someone built to fill it. There is one more layer to this that most people never reach. Runway orientation also affects noise impact on surrounding communities. A runway pointing toward a densely populated neighborhood means every departure climbs directly over thousands of homes. Every approach descends over schools and hospitals. Noise abatement procedures, specific turnout headings, reduced power segments, altitude constraints are designed to minimize exposure. But those procedures are limited by the fixed direction of the runway itself. When new runways are planned at existing airports, noise modeling is often as influential as wind data in determining the final orientation. A runway that provides perfect wind coverage but routes traffic over a city center may be rejected in favor of a slightly less optimal wind angle that keeps the noise footprint over industrial land or open water. The angle painted on the runway threshold is the output of a negotiation between meteorology, terrain, airspace, and the communities below. If you want to understand what happens inside the cockpit when the wind suddenly shifts during final approach, how pilots detect a wind shear event, what the escape maneuver looks like, and why low-level wind shear has caused more fatal accidents than almost any other weather phenomenon, I've covered that in full detail in another video.